Okay, in these notes we are going to talk about partial differential equations. Okay, so a partial differential equation is obviously an equation relating derivatives of a function, but this function has multiple variables, like this example. For instance, u has these two variables, t and x. And we can also have more variables, t, x, y, and so on and so on. So remember that the previous lectures we were studying ordinary differential equations, which where we have a function, but depending only in one variable, let's say x, and the derivative, some derivatives of this function that we don't know and we used to call u. Well, here we also call the function u, but the difference when we are talking about partial differential equations instead of ordinary differential equations is that we have more than one variable involved, as you can see here in these examples. And we have, of course, the derivative of these functions that they have a special notation because we have more than one variable, so we cannot say only, okay, let's work with the first derivative of this function. We have to be more specific because, okay, I have this function, for instance, u of t and x. I cannot say, okay, let's compute the first derivative of u, because what I'm saying when I say that, we are going to talk about the first derivative of u respecting to t, the first derivative of u respecting to x. So we have these possibilities. And we have a notation for that. We use this symbol of partial derivative. But to be honest, we are not going to use this symbol in these notes because I prefer just to use the alternative notation, which is a subscript. For instance, if I want to talk about the second derivative of u with respect to the variable x, then I will use this notation, u subscript xx, to talk about, I pick the function u, let's say this function, I derivate with this function, I differentiate this function with respect to x one time, so it's only 1x here, let's say, 1x here. And then that new function, I differentiate it again with respect to the same variable x. So we are going to use this type of notation. Okay. So, partial differential equations, we have a function that we don't know with more than one variable and some derivatives of this function. Let's see an example here. We have the wave equation, which is the second derivative with respect to t equal to a positive constant here, and the second derivative with respect to x of a function utx. Then we have the heat equation, which is the first derivative of u with respect to t, a positive constant, and the second derivative with respect to x of u. Then another example is the Laplace equation, which is for a function u depending on x and y, this the sum of these two second derivatives of u equal to 0. Okay, so as usual, as we did with ordinary differential equation, we can classify the partial differential equation. Remember some example, if we think about like people, we can also classify people in the sense like, okay, regarding age, let's say, or I don't know, where are they from, and etc. We have like different features to classify people, like nationality and etc. Okay, so the partial differential equation have the same. We look at the partial differential equation and they have some features that help us to classify them. and they are quite similar to the ones that we saw for ordinary differential equations. So we have the order, which is still the same as in the previous setting of ordinary differential equations, is the highest order derivative that appears in the equation. The dimensionality, which is the number of variables involved, and if we have an homogeneous or a non-homogeneous equation, which is whether there is a driving term or not, then we can see in an example of these features, but let's see these three examples. The order is 2 because the maximum, the highest order of derivative that appears is 2 in all these examples. Then the dimension is also 2. We have only 2 variables involved. And we don't have a driving term here. There is no other function as an independent term. So these three equations are homogeneous. Okay, so now we know what a partial differential equation is and how to classify them. What do we need to determine a solution? Because, okay, so far we have only the equation, and if we compare the situation with the ordinary differential equations, we used to have these initial conditions or to solve an equation, an ordinary differential equation. So now we have the analogon, which is boundary. We need boundary conditions and initial conditions. Okay, so let's try to see this example. We have this equation, which is the wave equation, with these boundary conditions and these initial conditions. Okay, we can think about the variable t as time, so we say initial conditions because in time 0, which is, let's say, the first time, we have that u at 0 x is fx, and this other condition with the derivative with respect to t. Okay, so we first try to classify this equation, which is order 2. Why? Because the highest order of derivative is 2. We can look at the second derivative with respect of x of u or t is the same. Then the dimension is also 2 because we only have 2 variables involved, t and x, and it's homogeneous. Homogeneous because there is no driving term. There is not an independent function, independent with respect to u, involved here in this equation. So we are here working with a 2-dimensional homogeneous PDE of order 2. And if we pay attention to the domain of this equation, we have an interval here from 0 to L and any positive time. So a picture of the domain of this equation, let's say, is this interval from 0 to L. And if we think as this variable as t, we have from 0 to infinity values that t can achieve. Okay, and here we have in green the initial conditions, and these purple are the boundary conditions. Okay, so one important difference with ordinary differential equations, where we only work with one variable, is that the initial conditions here are functions and not only numbers, as we work in the previous lessons with ordinary differential equations. So that's a huge difference, let's say, from the ordinary to partial differential equations. In future lectures, we will see how to solve this equation, but now just believe, trust me, that these two guys here are solutions of this wave equation. You can verify that. You just pick this solution, pick this candidate of solution, this function that I'm saying it is a solution, and we just compute the second derivative with respect to t and the second derivative with respect to x, and we check that these guys, both of them, verify the partial differential equation and the boundary condition. And we have here a dependence on n, where n can be 1, 2, 3, and so on. So we have many solutions. Okay, this solution have a name, normal modes, but we are not going to worry about the name of the solutions of these candidates. Okay, so observe that our partial differential equation and all of the partial differential equations that we will work on this in this course are linear, and this wave equation in particular is also a linear PDE. So we saw for the ordinary differential equation that if we have two solutions, then any linear combination is also a solution. Well, so we have that also here in this context where we are working with partial differential equation. So we also have this superposition principle where, okay, if you have all those solutions, any linear combination of them is also a solution. So we proposed, as usual, we suggest a solution of the form, okay, maybe my solution, the general one, the most general one I can give you, is any combination of those solutions that we found before, depending on n. And if we go back, let me go back just a little bit, here where we have these candidates of solutions, they both share this part, right? And then we have cosine here and sine here, depending on t, right? So any linear combination between these two guys, we have this factor in common, and that's why here in this expression where we say, okay, any linear combination of those two, we can write it like that, because we have this factor in common plus these two numbers, two constants that we don't know who they are any linear combination between those two. But okay, I have that this new guy is a solution for the wave equation and the boundary conditions for every n, okay? But then again, using the superposition principle, then any combination of these guys with different values of n is also a solution. And that's why we say, okay, I have that this is a solution for each n, then I try to pick all the n's I can. And that's why this is our candidate. Okay, so now remember that when we started this example, we have these three parts, let's say, the partial differential equation, the boundary conditions, and the initial conditions. So we found this u, forcing u, or maybe just proposing this solution that in the future we will see how to get them, and this u satisfies the partial differential equation and the boundary condition. So what remains is to verify the initial conditions, and that makes sense because we have this candidate of solution, but we have no idea who these numbers are. an and bn. We have no idea. We know that they are constants, but we don't know them. So we will use the initial condition to determine these values a1, a2, b1, b2, and so on. Okay, so the initial conditions were that u in 0, x is equal to f. And then if we go to our expression here, and we set t equal to 0, which is here and here, sine of 0 is 0, so this guy goes away, and cosine of 0 is 1. So that's why we finally get only this result. This an survived, and of course this factor that we have here. Okay, then with the second initial condition, which is the derivative of u with respect to t at 0, x is equal to g, we go here, we calculate, we compute. Remember that when we have a series, we can differentiate it term by term and integrate it term by term and add term by term. We can operate these functions term by term. So if we want to differentiate the function with respect to t, we do that term by term. So this guy doesn't depend on t, so stays like that. And this is the part that we actually have to differentiate. And okay, you can compute that, and then setting t equal to 0 in that new function, the derivative of this piece here, what we get is this other series with bn here, and this number that appears there because of the derivative of t, the derivative of u with respect to t, and still this factor is there because doesn't depend on t. Okay, so now depending on f and g, we will able to find these numbers a, n, and bn. Okay, so these guys here, this series, are called the Fourier sine expansion of f and g. That we will talk quite a lot about this Fourier sine expansion or Fourier series representation of functions. But we need some ingredients before really talking about this Fourier representation of functions. Okay, so in some cases it's quite easy to find these coefficients a, n, and bn. For instance, with this function f and g are just superposition of signs, like this example. For instance, imagine that f is this guy here, 3 sine minus 5 sine and g is equal to 0. Okay, g equal to 0 is quite easy. Then we go here and say, okay, then bn is equal to 0 for every n. And then putting this f equal to this expression, we can say, okay, look, when n is equal to 2, we have this term here, right? So we can have the identity of these two guys, this particular f and this series here, and we equate this coefficient by coefficient. So when n is equal to, that means that a2 in this case should be 3. And then when n is equal to 10, the coefficient A10 should be this minus 5 here. Sorry, minus 5 here. And there is no more signs here involved, so there is here we cannot see the sign when n is equal to 1, the sign when n is equal to 3, the sign when n is equal to 4, and so on and so on. So the only terms of the series that are here involved are only with n equal to 2 and n equal to 10. So then we can say, okay, the A2 is 3, the A10 is minus 5, and the rest of the terms are just 0. Okay? And that's what we have here. A2 is 3, A10 is minus 5, and then the rest are 0. And okay, which is 0 is just 0. Every Vn is 0. Okay. So sometimes we will be lucky and have this type of initial conditions, and it will be easy to identify these coefficients An and Bn. Sometimes we will not be that lucky, but before that we have to study a little bit some features on some functions. So the question is, how and under which assumptions can we express a general function f as a Fourier sine series? Okay, because I mean this is just a very particular case where it's almost it's super easy to identify the coefficients. But if I have any function f, can I write the function f as this Fourier series, Fourier sine series? Okay, well, the answer is not any function, but there is a family of functions that we will able to write as this series, and that's the next goal of this lecture.